Hello, this is Dr. Amudappriya, Associate Professor Triply from Rohini College of Engineering and Technology, Palkulam. We are discussing about the protection and switchgear course for the regulation 2017, and here we are discussing about the grounding methods in this lecture. First, let us see what is neutral earthing or neutral grounding and what is the need for grounding. Earthing is a process of connecting the electric conductor line to the earth through certain components which may offer a protection to the electric circuit. In earlier power systems, we used to have neutral ungrounded due to the fact that the first ground fault did not require the tripping of the system. Nextly, what they have done is they have detected that the ground detection system is favoring the short circuit impact reduction, etc. So as a result, there is a series resonant LC circuit which can create over voltages in excess to the LL fault when it is subjected to the repetitive re-strikes of one phase to the ground. This in turn has reduced the insulation life, resulting in possible equipment failure. In that cases, neutral grounding systems will be going wrong. It is misleading. So this is the case. And next, like fuses, they are blowing out. So how to reduce the impact? This is what is the main thing what they have discussed. And next, neutral grounding may offer a better one when the ground relays, I mean when circuit breakers are being provided and relay circuits are being provided through the, to the ground via this neutral grounding, and how they are limited, how long they are protecting the circuit from the fault instant which is occurring at that instant. So let us consider the importance of neutral grounding first. It can be used for both a low and medium voltage. It can protect transformers, generators, rotating machinery, etc. because they may have the star connection where neutral is being present. To the earth ground network, it being provided with the reference point of 0 volt, obviously. This protective zone measure offers advantages like the magnitude of the transient voltages may get reduced. So the ground fault locations can be easily simplified, and it may improve the protection level and reduce maintenance time and cost, greater safety for the personnel, and it improves the lightning protection and reduction in the frequency of fault occurrence. The method of neutral grounding are nothing but unearthed neutral system, solid resistance via resonance, and then earthing transformer, etc. For example, let us consider an ungrounded system. In this ungrounded system, there is no internal connection between the conductors and the earth. However, the impact of a capacitive coupling may be there. Since we are having the conductor and earth at different potentials, so we may have a capacitive impact. So under normal conditions, this distributed capacitance will cause no problem. In fact, it is almost a beneficial one to the neutral point. But during the fault condition, a ground fault on one line will result in full line-to-line voltage appearing through the system. Thus, a voltage of 1.73 times the normal voltage is present on all the insulation in the system. This situation can often cause failures in old motors, transformers, etc. due to insulation breakdown. So this is what is the case in an ungrounded neutral system. Advantages: after the first ground fault, assume it remains as a single fault, the circuit may continue in operation, permitting the continued protection until a convenient shutdown for maintenance, etc. It can be scheduled. But the main disadvantage is the interaction between the faulted system and the distributed capacitance. It will create transient over voltages. Upon second fault on another phase, when it occurs, before the first fault is cleared, there may be a destruction in the system due to LL faults, etc. Cost is high and it is complicated for locating the faults, etc. And next we are considering the solid neutral grounding. It is nothing but you are going to connect a conductor, plain conductor, from the neutral point to the earth without any connection of any component. So we can see that in this case, through solid neutral grounding, slightly it reduces the problem of transient over voltages. That is, when compared to the ungrounded system, it is better, and it provides a path for the ground fault in order to assign a range of 25 to 100% of the system three-phase fault. However, if the reactance of the generator or transformer is too great, the problem of transient over voltages will not be solved. When solidly grounded systems are an improvement over ungrounded system, their speed of fault location is better. They lack the current limiting ability of resistance grounding, and the extra protection has to be made up. To maintain the system safe and healthy, the transformer neutral is grounded, and grounding conductor must extend from the source to the furthest point of the system also. It also reduces the shock hazard to the person. These are some of the betterment. The system is not solidly grounded, the neutral point of the system will float with respect to the ground. So this connection has to be maintained properly. If the single phase earth fault system in a solidly earthed system may exceed the three phase fault current. So one way to reduce the earth fault current is to leave some of the transformer neutrals unearthed. So the main advantage is that solidly in this case is low over voltages, which makes the earthing design common at high voltages. Disadvantage is that it may involve the drawbacks and headsets causing maximum damage and disturbances. There is no service continuity, danger for personnel. While considering the application, it is applied for distributed neutral conductor and three-phase neutral distribution. While considering the resistance grounding, in this case, a resistance is connected to the line which is being connected from the neutral to the ground in order to reduce the burning and melting effects in the faulted electric equipment, to reduce the mechanical stress in the circuit, to reduce the electrical shock hazards, to reduce arc blast and flash hazard, to reduce momentary line voltage dip, to secure the control of the transient voltages, to improve the direction of the earth fault, and the grounding resistors, they are generally acting as per the Ohm's law, so that if the current is high, the voltage drops can be sufficiently managed with the help of this resistors. The resistors, due to which the short circuit current may also get reduced. As a result, the protection devices may not sense the fault. This is a main disadvantage, because the short circuit current may flow through the resistance also. So at that case, the sensing of the fault may miss. There are two different types of resistance grounding, which is low resistance grounding and high resistance grounding. So the ground fault current flowing through either type of the resistor when single phase faults to ground will increase the phase to ground voltage of the remaining two phases. You can see it here. So that the difference between the low resistance grounding and the high resistance grounding, that perception should be very clear before we are going for the analysis of the NGR current. So non-grounded neutral grounded resistor is highly essential in order to reduce the arc flash hazards which is associated with the phase-to-phase faults, and the arc flash hazards which may be associated with the LG faults also. So those NGRs has to be designed in such a way that the current blocking capability should be less than 50 to 100 amperes, and for high resistance grounding it should be above 100 amperes. So that design particulars has to be highly considered. Next, while considering the rating of the neutral grounding resistor, it has to depend upon the voltage, initial current and the timing. Low resistance grounding, its main advantage is it can limit currents up to 200 to 400 amperes. And high resistance grounding, it is mainly capable of considering limiting the current which may be 5 to 10 1 ampere to 2000 kVA of the system, right? Sorry, kA of this per 1 ampere per 2000 kVA system to 2 ampere per 2000 kVA system, which has a capacity of 4.16 kilovolt. So in this case, it reduces the arcing ground and it eliminates the arc flash hazards which has been associated with the LG ground, and this will eliminate the mechanical damage and thermal damage to a greater extent. And the phase limit currents, they may be self-cleared also in such a cases. But the main disadvantage is that it generates an extensive earth fall currents if it is combined with the strong or moderate capacitive connection to the so that the cost may increase, and hence also it requires a ground fault detection system in order to notify about the ground faults. Next, while considering the resonant earth system, it is nothing but we are going to add an inductive resistance, inductive reactance to the line which is being connected from the neutral to the ground. The speciality is that it may be considered as an inductive reactance, or we can include a Peterson coil or arc suppression coil or an earth fault neutralizer. So this is regarding its construction. While considering the operation, the Peterson coil is connected between the neutral point of the system and the earth and is rated so that the capacitive current in the earth fault is compensated by an inductive current which is passed through the coil. A small residual current will remain because this will be very small so that it can be eliminated, and minor earth faults such as a broken pin insulator that could be held on the system without the supply being interrupted. So transient faults would not result in supply interruptions. But the main advantage is small reactive earth fault current which is independent of the phase to earth capacitance of the system, and disadvantages cost is very high. Next is the earthing transformer. For cases where there is no neutral point available for neutral earthing, an earthing transformer may be used to provide a return path for single phase fault currents. In such a cases, the impedance of the earthing transformer may be sufficient to act as an effective earthing impedance. Additional impedance can also be added in series if required. A special zigzag transformer is sometimes used for earthing the delta windings to provide low zero sequence impedance and high positive and negative sequence impedance to the fault currents. Thank you. These are all the protection schemes which are being used for neutral grounding.